Hello, this is Reem from Exam Help Lab. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2 Variant 2 October-November 2019. Question number 1, Part A, distinguish between vector and scalar quantities. So, scalar quantity have only magnitude, whereas vector quantities have both magnitude and direction. Part B, the electric field strength at a distance x from an isolated point charge q is given by the equation E is equals to q by x squared b, where b is a constant. Part 1, use the definition of electric field strength to show that E has SI base units of kilogram, meters per ampere per centimeter cube. So electric field strength is equals to force divided by charge. Force is equals to mass into acceleration, and charge is equals to current into time. Mass has an SI unit of kg, while acceleration has meters per second square. Current is amperes and time is seconds. So now electric field strength has an SI unit of kg, meters per centimeter cube per ampere. Part 2, use the units for E given in B Part 1 to determine the SI base units of B. So when you rearrange your formula and make B the subject of the formula becomes Q by x squared E, where Q is ampere into seconds divided by meter square multiplied by kilograms meter per ampere per second cube. So now B has an SI base units of R, Question number 2, Part A, define acceleration. So acceleration is equals to change in velocity divided by time taken for that change in velocity. Part B, a steel ball of diameter 0.08 meters is released from rest. So at this point, initial velocity is 0 and falls vertically in air as illustrated in figure 2.1. A horizontal beam of light of negligible width is a vertical distance of 0.280 meters below the bottom of the ball. When it is released, the ball falls through and breaks the beam of light. Explain Part 1, explain why the force due to air resistance acting on the ball may be neglected when calculating the time taken for the ball to reach the beam of light. So air resistance, or you can say the friction force, can be neglected in the case where the weight of that object which is moving is far greater than the air resistance. So over here we can write compared to weight, air resistance is negligible. Calculate the time taken for the ball to fall from rest to position P, where the bottom of the ball touches the beam of light. So initially it was at rest, and the distance it is covering to reach position P is 0.28 meters. We have to find the time interval in which the ball reaches position P, and the acceleration is 9.81 since we are neglecting air resistance. So we can use the formula S is equals to ut plus 1 by 2 at squared. When you substitute your values, when you substitute all these values, you'll get the time taken as 0.24 seconds. Part 3. Determine the time interval during which the beam of light is broken by the ball. So, time taken for the ball to reach position P means it hasn't crossed the beam of light. So at this point, we can calculate the final velocity of the ball by using the formula v square is equal to u square plus 2as. We have the acceleration, which is 9.81, and the distance this ball is covering to reach position P. And we can find the velocity of ball when it reaches position P. So that will be equal to 2.344 meters per second. Now we can consider this final velocity of ball at position P, the initial velocity of ball at position P, so that when it crosses the beam of light, we can actually calculate the time taken for that ball to travel through the beam of light. So we can consider at position P its initial velocity as 2.344. Acceleration is still 9.81 as we are still neglecting a resistance. The distance now it has to travel to completely get past through the beam of light is actually the diameter of the ball, because right at this point this ball is gonna start moving through the beam of light, and when it crosses, it's basically covering its whole diameter. So we can write that the distance it will be covering is 0.08 meters, and we need to find the time interval for this. Now we can use again the same formula, as is equals to ut plus 1 by 2 AD square, and when you substitute your values, you'll get a time interval of 0.032 seconds. Part C. A different ball is released from the same position as the steel ball in part 1. This ball has the same diameter but a much lower density, means it has got the same volume but a much lower density. So lower density means lower mass this time, since they are directly proportional to each other according to the formula density is equals to mass divided by volume. For this ball, the force due to air resistance cannot be neglected as the ball falls. This time they're not neglecting the force due to air resistance. Now we need to state and explain the change which is going to occur to the time interval during which the beam of light is broken by the ball. So I should write that when density decreases, force of air resistance cannot be neglected because now its mass is much lower. Mass of ball is much lower than that of steel ball in part 1. Now when air resistance has come into action, they're not neglecting force due to air resistance in this part. The resultant force due to weight and air resistance both decreases. So we can write that resultant force decreases, and according to the formula, force is equals to change in momentum divided by time taken. When the resultant force decreases, time interval to get through the light beam increases. So we can write that time interval increases. Question number 3, part A, state Newton's third law of motion. So this is force on body A by body B is equal to the force by body A on body B, but opposite in direction. Part B, a block X of mass mx slides in a straight line along a horizontal frictionless surface. I must underline frictionless surface as shown in figure 3.1. The block X moving with speed 5v collides head-on with stationary block Y. So Y has an initial speed of 0 of mass my. The two blocks stick together and then move with common speed. So after collision, they're going to move with same speed as shown in figure 3.2. Part 1, use conservation of momentum to show that the ratio my by mx is equal to 4. So conservation of momentum tells that momentum before and after collision is equal. So before collision, momentum is mass of x multiplied by its velocity plus mass of y multiplied by its initial velocity, which at 0 is equals to momentum after collision. So both mx and my now have a common velocity v. So now when you rearrange your formula and bring my by mx, first let me write this, we'll simplify it. So v and v on both sides get cancelled. Now it's 4mx is equals to my. And just like our question asked us to prove that my by mx is equals to 4. Part 2, calculate the ratio total kinetic energy of x and y after collision divided by total kinetic energy of x and y before collision. So kinetic energy is equals to half into mass into speed square. Total kinetic energy of x and y after collision will be half into mass of both x and y, let's bracket them, into their final speed, which is v square, and total kinetic energy of x and y before collision. So separately I will be calculating of mx and my. So this was 5v in the whole square plus kinetic energy of y before collision. Since y was at rest, so it didn't have any kinetic energy. So now total kinetic energy of x and y after collision is and total kinetic energy of both x and y before collision and that this one is over here is 0 since it wasn't moving. So now this is total kinetic energy of x and y after collision divided by, so I will reciprocal it, and 25v square mx. This 2 and 2 gets cancelled. This v square and v square gets cancelled. So we are left with mx plus my divided by 25 mx. Now making it simpler, mx and mx gets cancelled. So I'm left with 1 by 25 plus, we proved in the previous part that my by mx is equals to 4. So I'm left with 4 by 25. And when you add them, you'll get a ratio of 0.2. Part 3, state the value of the ratio in part 2 for a perfectly elastic collision. So a perfect elastic collision will have conservation of both momentum and kinetic energy. So for a perfectly elastic collision, my ratio of total kinetic energy of both moving objects before collision and after collision will be 1. So over here I'll write 1. Part C, the variation with time t of the momentum of block X in part B is shown in figure 3.3. Block X makes contact with block Y at time t is equals to 20 milliseconds, so I should highlight this. Part 1, describe qualitatively the magnitude and direction of the resultant force, if any, acting on block X in the time interval t is equals to 0 to t is equals to 20 milliseconds. Okay, so a horizontal line means there is no resultant force since change in momentum is equals to 0. So we can write resultant force is equals to 0. From t is equals to 20 milliseconds to t is equals to 40 milliseconds, from here to here, a straight line with constant gradient, which basically tells you the resultant force, that is change in momentum divided by time taken, means there is constant resultant force acting on block X. So constant resultant force. Part 2. On figure 3.3, sketch the variation of the momentum of block Y with time t from t is equals to 0 to t is equals to 60 milliseconds. Okay. So even though this case isn't of elastic collision, means kinetic energy is not being conserved, but momentum is. This means combined momentum before collision and after collision stays the same. Momentum of block Y is 0 before collision, as it is stated in question in the beginning that it's at rest prior to collision. So I'll draw a line on x-axis until t is equals to 20 milliseconds. So here I have drawn a horizontal line on the x-axis until t is equals to 20 milliseconds. Now, according to law of momentum, block Y's momentum should increase because that of block X decreased from in the time interval of t is equals to 20 milliseconds to t is equals to 40 milliseconds. Block X had change in its momentum for 20 milliseconds until t is equals to 40 milliseconds. It will be the same for block Y, except that it will have a positive gradient because its resultant force is in the opposite direction to that on block X, but of the same magnitude. So now I had a difference of 1, 2, 3, 4, and 5 boxes of difference between this line and this line. So I should end my line right here so that I will have a difference of again 1, 2, 3, 4, 5 boxes from this height. So I should have a straight line reaching up till this point and then straight line until t is equals to 60 milliseconds. Question number 4, part A. A sphere in a liquid accelerates vertically downwards from rest. For the viscous force acting on the moving sphere, state part 1 the direction. So this sphere is moving vertically downwards, means the viscous force, which is basically the friction force, or it is a force which is going to act against the motion of the sphere. So viscous force will be acting upwards. Part 2, the variation, if any, in the magnitude. So viscous force increases with increase in depth. So the more the sphere goes into the depth of the liquid, the higher the viscous force will be. So it increases. You should write completely that viscous force increases. Part B, a man of weight 750 newtons stands a distance of 3.6 meters from end D of a horizontal uniform beam AD as shown in figure 4.1. The beam has a weight of 380 newtons and a length of 9 meters. The beam is supported by a vertical force at pivot B and a vertical force at pivot C. Pivot B is a distance of 2 meters from end A, and pivot C is a distance of 2 meters from end D. The beam is in equilibrium. So part 1, state the principle of moments. So to remain in equilibrium, total clockwise moment about a point is equal to total anti-clockwise moment about the same point. Part 2, by using moments about pivot C, calculate force at B. So point C is that point about which total clockwise and anti-clockwise moments are going to be equal. About pivot C, so there are 3 forces acting about C: the weight of this human being, the weight of the beam, and the force at B. So total clockwise moment is equals to mass into velocity, and the mass which is causing clockwise moment is force at point B, since it's going to move clockwise. So, and the perpendicular distance between force B and the pivot C, the distance is 9 minus 2, which is 7 meters from B to D, and then 7 minus 2, that will give you 5 meters. So 5 meters is the distance between force at point B and the pivot C. So mass is FB into 5. Total anticlockwise moment. Now the masses which are causing anticlockwise moment are the 750 Newton weight of this human being and 380 Newton weight of the beam. The perpendicular distance between this weight of the human being and pivot C is 3.6 minus 2, which is 1.6 meters. The total distance between the weight of the beam until D is half of 9, since the weight will be acting from the center, right from the center. It's half the length of the beam, which is 4.5 meters. Now 4.5 minus 2 will give you this distance, which is 2.5 meters. So total anticlockwise moment is equals to 750 into 1.6 plus 380 into 2.5. Now when total clockwise moment is equals to total anticlockwise moment, you'll have a value of force at point B as 430 newtons. Part 3, the man walks towards end D. The beam is about to tip when force at B becomes 0. Determine the minimum distance x from end D that the man can stand without tipping the beam. So the man has now moved towards D. Now the newer diagram will look somewhat like this. This is end A and this is end D. This is the center, which is the weight of the beam. This is pivot C. And then now the man has moved towards point D and has a weight of 750 newtons acting downwards. And force at point B has become 0. So now we have got only two forces acting about point C. So again, the perpendicular distance between point C and the weight 380 newtons is 2.5 meters. And this is the distance which we need to find in order to keep this beam in equilibrium. So now the rule is that total clockwise moment about point C should be equal to total anti-clockwise moment about the same point, which is C. So 750, which is the weight of that person, into distance between that man and the pivot point C, should be equal to the moment due to 380 newtons, the weight of the beam. So 380 into 2.5. This is equal to 1.267 meters. But hold on, this is not what we were asked to find. This is the distance between that man standing towards D and the pivot point C. And the question is asking us to find the minimum distance from end D that the man can stand. So what we got is actually this distance, and what the question is asking is this distance. Now we know from point D until pivot C is actually 2 meters, and we have found this much of distance, which is 1.2667. So now we need to find this distance, which is x. So we will subtract 1.2667 from 2 to get the value of x, and this is equal to 0.7 meters. Question number 5, part A, state what is meant by the wavelength of a progressive wave. So this is distance between two adjacent wavefronts. Part B, cathode ray oscilloscope is used to analyze a sound wave. The screen of the CRO is shown in figure 5.1. The time-based setting of the CRO is 2.5 milliseconds per centimeter. Determine the frequency of the sound wave. So frequency is equals to 1 by t, and t over here is the time period, means the time taken for one complete wave. Okay, so one complete wave is from here until here. This whole wave in total is covering 10 small square boxes. By small square boxes, I mean these small square boxes. So, and 1 centimeter, you can see that it is comprising of 5 small square boxes. So 1 centimeter is equals to 5 boxes. And I told you that this whole wave is taking 10 small boxes. This means that it is covering 2 centimeters of distance. So it says that 2.5 into 10 to the power of negative 3 seconds for each centimeter. And we have got 2 centimeters, so we'll multiply 2.5 into 2 to get the time period. And when you divide 1 by 2 into 2.5 into 10 to the power of negative 3, you will have a frequency of 200 Hertz. Part C, the source emitting the sound in part B is at point A. Waves travel from the source to point C along 2 different paths, AC and ABC. So this is the direct path from A to C, and this is the indirect path to reach point C. They have the same finishing points and they have the same starting points. The difference is in the paths they're taking to reach point C. Distance AB is 8 meters and distance AC is 20.8 meters. Angle ABC is 90 degrees. Assume that there is no phase change of the sound wave due to the reflection at point B. The wavelength, okay, so the wavelength of the waves is 1.6 meters. Part 1, show that the waves meeting at C have a path difference of 6.4 meters. So for this, we must have distance BC, which is this one. So by using the Pythagoras theorem, that AC square is equals to AB square plus BC square. So after you substitute all your values, you will have BC's length as 19.2 meters. Now that you have the BC's length, you should get that the total indirect distance, the total distance of ABC is equals to 8 meters plus 19.2 meters, which is equal to 27.2 meters. And the distance it covers directly from A to C is equals to 20.8 meters. Now the path difference is basically the difference between these two distances. So path difference is equals to 27.2 minus 20.8. And this is equals to 6.4 meters. Part 2, explain why an intensity maximum is detected at point C. So intensity maxima forms only when 2 incoming waves are in phase and they form constructive interference. Also, their path difference isn't in fractions, means the path difference is in the whole numbers, like a path difference of just 1 wavelength, path difference of just 2 wavelengths. So I can reason that the incoming waves at C are in phase. They form constructive interference. And the path difference between both those waves in this case is 4 lambda, since the path difference is 6.4, and when you divide your path difference with the wavelength, which is 1.6 in this question, that will give you your path difference, which is 4 times of lambda. 4 times wavelength is the path difference between the distances being covered by the sound wave to reach point C. Part 3, determine the difference between the times taken for the sound to travel from the source to point C along the 2 different paths. So time is equals to distance divided by speed. We'll also need to calculate speed of sound wave. So speed is equals to lambda, which is wavelength, into frequency. The wavelength is 1.6 and the frequency from the previous part, we couldn't use that, into 200, and we have the speed of sound as 320 meters per second. Now we will first calculate the time for ABC, which is the indirect route, and the total distance it was covering is 27.2 divided by 320. We'll have the time as 0.085 seconds. And now the time taken for the same sound wave to travel directly from A to C is, the distance A to C is 20.8. So 20.8 divided by 320, and this gives us 0.065. So it took longer, obviously, on ABC route. So now the time difference is 0.085 minus 0.065, and the time difference is of 0.02 seconds. Part 4. The wavelength of the sound is gradually increased. Calculate the wavelength of the sound when an intensity maximum is next detected at point C. Okay, so the main point you need to look through is that they're asking you to find the wavelength when the next intensity maxima forms. So intensity maximum, and maxima can only form if the path difference is in the whole numbers. That is, if the path difference is like 1 wavelength, 2 wavelength, 3 wavelength, or 4th wavelength, and then it continues. So the path difference is not in fractions like half of wavelength, or 3/2 of wavelength, or quarter of wavelength. So when they have told you that the wavelength has increased, the path difference would decrease from 4 lambda to 3 lambda, because that's the only way next possible maximum can form. And the next to 3 lambda even will be 2 lambda. So they're asking us to find the wavelength when the second maxima is possible to be detected. So our answer would be 3 lambda. It will decrease from 4 lambda because 4 lambda was in part 1, and now 3 lambda is equals to 6.4, and then your newer wavelength is 2.13 meters. Question number 6, part A, state Kirchoff's first law. So Kirchoff's first law is the conservation of current. So I can write that sum of currents entering a junction is equal to sum of currents leaving that same junction. Part B, the variations with potential difference V of the current I for a resistor X and for a semiconductor diode are shown in figure 6.1. Part 1, determine the resistance of the diode for a potential difference V of 0.60 volts. So at 0.60 volts, there is 7.5 milliamperes of current, which is basically 7.5 into 10 to the power of negative 3 amperes of current. Formula for resistance is voltage divided by current. At 0.6 volts, you have 7.5 into 10 to the power of negative 3 amperes of current, and that gives you a resistance of 80 amperes. Part 2, describe qualitatively the variation of the resistance of the diode as V increases from 0.6 volts to 0.75 volts. Now, when you calculate, when you start taking the gradient on this graph of diode, which is not an ohmic conductor, you'll see that your gradient starts to decrease. So I can say that resistance decreases because gradient of this graph gives you nothing but resistance. Part C, the diode and the resistor X in part B are connected into the circuit shown in figure 6.2. The cell has electromotive force E and negligible internal resistance. Resistor Y is connected in parallel with resistor X and the diode. The current in the cell is 9.3 milliamperes and the current in the diode is 7.5 milliamperes. Part 1, use figure 6.1 to determine E. So EMF E of the cell is going to be equal to the voltage in each loop, means this first loop and then this second loop. And this is the rule in parallel circuits, that voltage of the supply is going to be the voltage in each of the loops. This means that PT across diode and resistor X is going to be equal to EMF of the cell. Now when we look at figure 6.1, you will see that when current across X and diode is 7.5 milliamperes, PD across resistor X is 0.3 volts and PD across diode is 0.6 volts. So combined PD across X and diode is equals to 0.3 volts plus 0.6 volts, and this gives us a value of 0.9 volts. Now I'll repeat that PD across either of the loops is going to be equal to the EMF of the cell. So 0.9 volts is the PD across this first loop, means combined PD across this diode and resistor X is 0.9 volts. This means that EMF E of the cell is also going to be 0.9 volts. But to determine the resistance of resistor Y, so formula is R is equals to V divided by I. Since EMF E is 0.9 volts, this means that voltage across resistor Y will also be 0.9 volts. And current across resistor Y will be the difference between 9.3 and 7.5, since current divides in parallel circuits. The current entering these two loops is 9.3. The first one which gets divided at this end is 7.5, means here comes 9.3 minus 7.5 milliamperes, which is 1.8 milliamperes. Now that we have the voltage, which is 0.9 and 1.8 milliamperes, which we will convert to amperes, and then you will have the resistance of 500 ohms. Part 3, calculate the power dissipated in the diode. Power dissipation has its formula I square R. Since they are asking us to get the power dissipation in the diode, so resistance of the diode and current across diode. Now current across diode is going to be 7.5, and so will the current across resistor X, because current stays the same in components which are connected in series. So current across diode is 7.5 milliamperes, and the resistance across diode when the current across it is 7.5 can be deduced right from here. 7.5 milliamperes, the diode has a voltage of 0.6 volts across it. So when current is 7.5 milliamperes, resistance of Y is going to be equal to what we calculated in previous part, that resistance of diode when current is 7.5 milliamperes and voltage is 0.6, it has a resistance of 8, since the resistance is changing for diode at each point and it is decreasing by the time it reaches its height. Part 4, the cell is now replaced by a new cell of EMF 0.5 volts and negligible internal resistance. Use figure 6.1 to determine the new current in the diode. So now the EMF E has changed its value, has decreased its value from 0.9 to 0.5 volts. Now according to parallel circuits rule, EMF of cell E, which is now 0.5 volts, is going to be equal to PD across this loop, meaning PD across X and PD across diode give sum of 0.5 volts. So voltage entering this loop, this first loop, is going to be of 0.5 volts, and then the voltage leaving this loop will also be of 0.5 volts, while current is going to be constant for both these components, diode and resistor X. So current across diode is going to be equal to current across resistor X. Now we need to look through the graph that at which value of current the two voltages will give us the sum of 0.5 volts. So 0.5 volts can be achieved by either 0.3 and 0.2 or 0.4 and 0.1. While 0.2 and 0.3 also give 0.5 volts of total PD, but they give different values of currents. Hence, it's going to be 0.1 volt and 0.4 volts, since at 0.1 volt resistor X has a current of 2.5 milliamperes running through it, and again at 0.4 volt or at diode, it will be having 2.5 milliamperes of current running across it. So this fulfills our requirement. Now we can write that there is going to be 0.4 volts and 0.1 volt, and the voltage and the current across diode will be 2.5 milliamperes. So the two values which give us the final voltage of 0.5 volts, they have the constant current value of 2.5 milliamperes. Question number 7. A nucleus of plutonium-238 decays by emitting an alpha particle to produce a new nucleus X and 5.6 mega electron volt of energy. The decay is represented by the following equation. Part A, determine the number of protons and the number of neutrons in nucleus X. So since alpha particle has been released and alpha particle has a mass number of 4 and a proton number of 2, so for X the proton number will decrease by 2 from plutonium, and that will be 92. And since alpha has a nucleon number of 4, X will have a nucleon number of 234, and then 234 minus your proton number will give you number of neutrons, and hence number of neutrons will be 142. Part B, calculate the number of plutonium-238 nuclei that must decay in a time of 1 second to produce a power of 1.15 watts. So power has a formula of number of nuclei multiplied by the energy divided by time taken. Since we are given with power and we are also given with time and energy, we will first need to convert the energy in mega electron volt to joules, because that's the SI unit. So 5.6 mega electron volt to first electron volt. So this will be 5.6 into 10 to the power of 6 electron volt. Each electron volt has 1.6 into 10 to the power of negative 19 joules of energy. So 5.6 into 10 to the power of 6 electron volts will be equal to 5.6 into 10 to the power of 6 into 1.6 into 10 to the power of 9 minus 19 joules of energy. Now that we have the power 0.15, time is 1 second divided by the energy in the joules. These are the number of plutonium-238 nuclei, and this will give us 1.67 into 10 to the power of 11 number of plutonium-238 nuclei. Now we are done with this paper. Thank you for watching.